Welcome to Trig 10. So today we're going to be learning about how to prove trigonomic identities. So there's going to be a lot of different ways that you guys could go about this. There's not any one correct way to do them. So that's where it could be like a little bit more challenging because it's not going to be just straightforward to the point. There are different orders you could do them in. There are different ways you could do them. But in the end, you should be able to get it to equal the other side. You should be able to prove the identities. Okay, so everyone's might look a little bit differently, but in the end, we should be able to get to where we want to be. These are giving you guidelines to verifying trigonomic identities. So this is giving you a plan of attack to how to approach these types of questions. So the first thing you guys want to do is you want to pick just one side of the equation to work with. You always want to start with the more complicated side. Okay, so the one that looks more difficult, start with that side. You're going to simplify your chosen side until it's identical to the other side. Do not work across the equal sign. So that's the biggest thing is my students want to do things to both sides of the equal sign. No, you're picking one side and you're only manipulating one side. You are not allowed to work across that equal sign. A good tip is if you can change every expression into terms of sine or cosine. Look for algebraic operations that you can perform, such as adding fractions, factoring something out, distributing, squaring terms, multiplying by conjugates, multiply by terms, multiply by a clever form of 1. So all of these algebraic options can help us manipulate one side of the equation. You're going to look for trigonomic things you can do as well. So if there's squares of functions, you need to think Pythagoreans. So I always say that if there's squares or ones involved, we're dealing with a Pythagorean identity. Remember that cosine times secant or sine times cosecant or tangent times cotangent always equals 1. Keep looking at the answer. That's your goal, to make sure you're on the right path. So keep looking at your answer and am I getting closer to that answer? Remember, there will often be more than one way to verify an identity. Don't quit. So that's what I was saying in the beginning. There's going to be a lot of different ways, and the way you do it and the way I do it could be completely different. As long as you're still using proper properties and you are manipulating and you get the answer, you're fine. So don't quit. If one idea doesn't work, try something else. There's been many times I've been trying to prove an identity, and then I'm like, okay, this isn't really leading me to where I want to go. So then I just nix that idea, and then I try something else. I try manipulating using something else. And then when you are finished, you're going to put QED. I call it QUED. That's not like technical or correct or anything like that, but it means quod erat demonstratium, which I don't know how to say that properly, but it just means that I have demonstrated this. So I have demonstrated that these two are equal to each other. I have proven my identity and I'm done with my proof. All right, so we're going to just start with a basic algebraic proof, just so you guys can see how this works with algebra, and then we'll move into trig. So step 1, pick your more difficult side. Obviously, the difficult side in this one is your left side. 2 is not difficult, so I'm going to pick the left side. You can only manipulate the left side. You cannot multiply, divide, you cannot do anything across the equal sign. So my goal here is to make this side, my left side, equal to. Okay, so I want to make my left side equal to. Okay, so just look at options that we have here. I'm going to pay attention that both of these numerators are difference of perfect squares, so I'm going to go ahead and factor my numerators. So I'll get x plus 1, x minus 1 over x minus 1 minus x minus, I'll do it in the same order, plus 1, x minus 1 over x plus 1 equals, I just put the equals and don't even worry about equals to, just put equals. So you just keep manipulating this side. You cannot do anything to the right side. Okay, so now I can clearly see that I will be able to cancel these guys. So now I have x plus 1 minus x minus 1 which equals, again, just putting that equals, and I'll actually line up my equals, which equals. Okay, next thing I'm going to do is I'm going to go ahead and distribute. So I get x plus 1 minus x plus 1 equals. And then we simplify x minus x. And then we have 1 plus 1 is 2, which equals my left side, which is 2. So I just proved that these do equal each other. So now we put qued. I have demonstrated that these are equal to each other. So qued. Okay, so that's how it works. You pick a side, you manipulate the one side to make it look like the other side. Okay, so let's go ahead and move on to doing one that has trig. Okay, so the first thing I'm going to personally notice about this one, and if you guys have your trig chart downloaded, here's mine. Download this trig chart, print it if you have a printer. This is pretty much like a cheat sheet to all of our different identities that we can use to manipulate. Okay, so it has everything on these 2 pieces of paper. So I posted this in my first trig module, so make sure you guys download it, you have it available, you print it, however to use this. We're going to use this. Okay, so we're going to work the left side. The left side is more difficult than the right side, right? I have 1 over cosine squared b minus 1 equals tangent squared b. Okay, so we're going to work the left, and we're going to try and get it to equal tangent squared b. Okay, whenever I see squares and ones, I'm talking about a Pythagorean identity. So if we look at this, here's my Pythagorean identities. And we want to figure out which one has tangents, and it's going to be secants because we know 1 over cosine squared b is the same as secant because of the reciprocal function. So here's my reciprocal functions. So we know 1 over cosine is really the same as secant. So that's how I'm going to start. So 1 over cosine squared is really just secant squared beta minus 1 equals. Okay, so again, if I have squares and ones, I'm definitely talking about a Pythagorean identity. And I'm talking about this Pythagorean identity right here. Okay, it doesn't look exactly the same, so I'm going to go ahead and write this down. Tangent squared theta plus 1 equals secant squared theta. So our Pythagorean identity is tangent squared theta plus 1 equals secant squared theta. So now my goal is I want this to look identical to this. So this is secant squared beta minus 1. So what do I need to do to make those look identical is I need to subtract 1 from both sides. So if I subtract 1, I get tangent squared theta equals secant squared theta minus 1. And now notice these are identical. Identical, identical. So what is secant squared beta minus 1 equal to? It's equal to tangent squared theta. Or we're using beta. So tangent squared beta. And I just proved this. So we put qued. Okay, so again, what I used. This reciprocal function to get my secant squared. Then I used my Pythagorean identity, tangent squared theta plus 1 equals secant squared theta. I made it look just like this, and then I got that it's equal to tangent squared beta. So this side is equal to this side. I proved it. Okay, let's look at 3. How to tell which side's more difficult. Whenever you have pluses and minuses, that's going to be a more complicated side. So since this left side has the plus, that is going to be more complicated. Okay, so let's look at our answer. And we're always looking back to our answer to kind of see what we're trying to get. So I need secants and cosecants. Secant and cosecants, which are reciprocals of sines and cosines. So this relates to sine and cosine, so I want these to relate to my sine and cosine. So what do I know about tangent and cotangent that could be rewritten in terms of sine and cosine? So again, if we look at our trig chart, and if you guys look at the quotient identities, we know tangent and cotangent are the same as sine over cosine or cosine over sine. So I am going to replace tangent and cotangent with sine over cosine and cosine over sine. So step 1, tangent is really the same as sine x over cosine x plus cotangent's the same as cosine x over sine x, which equals, just put which equals. All right, so now I have it in terms of sine and cosine. Now I want to be able to add these together because if we notice, this doesn't have any pluses or anything. So we want to add these together. We want to combine it into one fraction. So in order for me to combine fractions, we need common denominators. So my common denominator between cosine and sine would just be cosine times sine. So that means this one needs to be multiplied by a sine of x, top and bottom, and this side would have to be multiplied to a cosine of x. Okay, so now I can write these all over the same denominator, which is going to be sine of x times cosine of x. Okay, so I multiply the top. Sine x times sine x is sine squared x. Cosine x times cosine x, cosine squared x, and we're adding these together. Equals, and leave it. Okay, whenever we have squares, we are talking about a Pythagorean identity. This is your main Pythagorean identity. The main Pythagorean identity is sine squared x plus cosine squared x equals 1. So I know that sine squared x plus cosine squared x is equal to 1. So this numerator is 1. So now I get 1 over sine x cosine x. Okay, we're really close to the end. So notice my answer is secant and cosecant. Well, we know 1 over sine is the same as cosecant, and we know 1 over cosine is the same as secant. So I'm going to rewrite this, and I'm going to put it in the right order. So I'm going to do 1 over cosine of x times 1 over sine of x. So now using our reciprocal functions, so again, here's our reciprocals. Using our reciprocal functions, we know 1 over sine is cosecant, and we know 1 over cosine is secant. So now I can replace those. So 1 over cosine is secant. So secant x times 1 over sine, cosecant x, which is equal to secant x times cosecant x. So I just proved that this left side is in fact equal to the right side. So again, when we have proved this, we put qued to prove. I have completed this proof. I proved it. I demonstrated that they are the same. All right, let's look at number 4. Okay, so this one says match the function with one of the following. So pretty much we're going to manipulate this, and hopefully it's going to look like either this or it's going to look like this. Okay, this is one. Again, we're going to start off with math stuff. Okay, I'm going to go ahead and I want to combine this so I can add these together. So we want a common denominator, and obviously my common denominator is just multiplying these together. And I hope you realize when we multiply these together, we have conjugates, right? Because this is secant x minus 1, secant x plus 1. Conjugates have the opposite sign. So when we multiply them together, it's just first times first, last times last. Okay, so step 1, get ourselves a common denominator. So that means I need to multiply this one by secant x minus 1, secant x minus 1, and this one has to be by secant x plus 1, secant x plus 1. So we're getting our common denominator. Okay, so we're going to multiply together my denominators. So again, when I get this common denominator, these are conjugates. So I'm doing secant x times secant x, which gives me secant squared x. And then I get 1 times -1 is just -1. So now my denominator is secant squared x minus 1. Numerator, I would have secant x plus 1 plus secant x minus 1. All right. Okay, so again, I can see that I can just combine like terms on my numerator, and on my denominator, whenever I have squares and ones, that's a Pythagorean identity. And I think this is the one we already talked about, secant and tangent, yeah. So I'm going to combine my like terms, and this is my Pythagorean identity. Okay, so handling the numerator, secant x times secant x plus secant x is 2 secant x's, and 1 minus 1 is just, they eliminate each other. Over, so now let's see what secant x minus 1 is the same as. So I go to my Pythagorean identities. Again, I'm using this one, and we want it to read secant x minus 1. So to get it to look like that, I would subtract 1 from both sides. So then I get tangent squared theta is equal to secant squared theta minus 1. So secant squared theta minus 1 is the same as tangent squared theta. So we're going to replace it with tangent squared theta. Tangent squared, not theta, we're using x. Tangent squared x. Okay, so it's looking better. It's condensing. It's getting smaller. It's not as complex. So we're going to keep going because, again, my goal is to either make it look like this or to make it look like that. Okay? I can right here kind of assume which one it's going to be, and I can kind of assume that because of this right here that has the number 2, and this has a 2, because I don't really see a way where a 2 is going to disappear, but let's just keep manipulating it. So what I'm going to go ahead and do is I'm going to pull these apart so we can see it better. So this is really 2 times secant, that s is ugly, so 2 times secant x, okay, times, and then we're going to write this as 1 over tangent squared x, like so. Okay, let's go even further. Maybe my plan of attack here, and this is always a good plan of attack, is to start changing things to sines and cosines. That usually, for the most part, will help you out. So I have secants and tangent squares. I am able to change these all into sines and cosines. So that's what I'm going to do next. So I'm going to do 2 times secant is really 1 over cosine of x. And 1 over tangent squared is the same as cotangent squared. So I'm just going to do that. Okay, still with the goal in mind that we're going to change these to sines and cosines. So this one already has a cosine. This I want to change to cosines and sines. So we know per the quotient identity, cotangent is cosine over sine. So that's what I'm going to do next. So I have 2 times 1 over cosine x. Cotangent, I'm going to do cosine squared x over sine squared x. Okay. We can see here, now we can simplify. This cosine goes by with one of these. So now let's see what we have. So now we have 2 times, I have a cosine in the numerator, and I have a sine squared x. Okay, again, if we look at our answers here, there's no squares in my answers. So we want to kind of break apart this sign. So we could break this part into, or this sign into sine of x times sine of x. We know sine of x times sine of x is sine squared x. So that's what I'm going to go ahead and do next. I'm going to take this and break this into 2. So I'm going to get 2 times cosine of x over sine of x times 1 over sine of x. Again, we haven't changed anything because when I multiply this together, I'll still get sine squared x. And when I multiply this together, I'll still get cosine x. Okay, now we are to a point I hope you guys can see our clear answer is A. Okay, because now it's 2 times cotangent. Well, cotangent is cosine over sine, so there it is. This is cotangent. And 1 over sine is the same as cosecant due to the reciprocal function, or the reciprocal identity. So we're going to get 2 cosine over sine is cotangent of x, and 1 over sine is cosecant of x. So we were able to solve that, and it matches A. And again, I kind of knew it was probably going to be A once we got this 2, because I don't really know how we would have eliminated a 2, but here's the whole process. All right, let's try our next one. Okay, this one, honestly, you could go either way with which side's more difficult. I think the left is still more difficult because I have 3 different things going on over there. So I'm still going to choose my left. Remember, you are able to choose the less difficult. It's just harder to come up with things to manipulate it to make it more complicated. It's always easier to get more simple than to get more complicated. So I'm still going to pick this side to manipulate. Okay, so I'm gonna approach this with the idea of let's change things to sines and cosines, since most of it's already sines and cosines. So I'm gonna go sine squared theta cosine theta. Secant is really 1 over cosine theta, which equals. We can see here that these are going to cancel each other out. So now I just have sine squared theta. And we need the other side to be 1 minus cosine squared theta. And we can do this with a Pythagorean identity. Okay, so let's look at our Pythagorean identity. So the ones that have sines and cosines, this one, I want to know what sine squared theta is equal to. So to get sine squared theta by itself, I would subtract a cosine squared theta, and then I'd do 1 minus cosine squared theta, so I'm subtracting it from both sides. So then I would get sine squared theta is equal to 1 minus cosine squared theta. Okay, so sine squared theta is equal to 1 minus cosine squared theta, so that's what I would write next. That's equal to 1 minus cosine squared theta, which we made it equal the other side, 1 minus cosine squared theta. So I proved this, so we put qued. Okay, so hopefully you guys are kind of starting to see some things. Okay, this one. And it gives us a note to help us with this one. So again, looking at this one, it's like, I don't really know which one's more difficult. But since the left side has an extra term in the denominator, it makes it more complicated. So this one is more complicated because this denominator is more complicated. So this is my complicated side. Okay, so again, this is my complicated side. So I'm going to manipulate left. All right, so where to start with this one? Not really sure. So this one, I'm going to identify, and this happens a lot as well. If I had 1 minus sine squared x, then I would have a Pythagorean identity. But since this isn't squared, I do not have a Pythagorean identity. We like Pythagorean identities because we know that that's an identity and I can manipulate with it. So is there a way that I can create this to be a Pythagorean identity? And there is, by multiplying this by its conjugate. So I'm going to go ahead and multiply the top and bottom by 1 plus sine t. So again, I'm going to do 1 plus sine t. Okay, so remember when we multiply conjugates, we do first times first, last times last. So I get first times first is 1, last times last would give me negative sine squared t. And then my numerator would be, do we want to distribute it? I'm not going to distribute it. We'll see what it looks like. Maybe we will. Cosine of t times 1 plus sine of t. And we see I don't want to distribute this because if I look at my other side, there is this 1 plus sine of t. So I'm thinking, okay, I don't want to distribute that. So equals. Okay, so now we have 1 and a squared, so this is a Pythagorean identity. And again, this is going to be using sine squared theta plus cosine squared theta equals 1. So I'll write it out over here. So we have sine squared theta plus cosine squared theta equals 1. That's our main Pythagorean identity. I want it to read 1 minus sine squared, so I'm going to subtract my sine squared theta from both sides. So now I get cosine squared theta is equal to 1 minus sine squared theta. So where that 1 minus sine squared theta is, we can put cosine squared. So now I have cosine of t, 1 plus sine of t, over, and this is cosine squared of t. Okay, now we can see we can just simplify one of these with this. And once I simplify, I have 1 plus sine of t over cosine of t. And that is my right side, so I did prove it. Sine t, cosine of t. Like so, we proved it. We're going to put qued. Again, I don't know if qued is a real thing. I just call it that. It sounds cool. All right. I think you guys should pause the video and try to do example 7 on your own. Okay, so for example 7, obviously this left side is much more complicated than the right side, so I'm going to mess with the left side. I'm just going to observe it first and see what's happening here. So first thing I'm going to observe is that I have sine squared x. We know right away that this is a Pythagorean identity and that I can convert that to being 1 minus cosine squared. So if I wanted sine squared, we would subtract the cosine. So then I get 1 minus cosine squared. So that's what I'm going to start with. So we have 1 minus sine squared x is really 1, I'll put it in parentheses, 1 minus cosine squared x over 1 plus cosine squared, not cosine squared, just cosine x, equals. This 1 minus is on the outside. Let me kind of draw that better. 1 minus. So really what I'm doing right now is I'm just going to worry about manipulating this as far as I can, and then I'll deal with this. Okay, so this is difference of perfect squares. This is a perfect square. This is a perfect square. We know how to factor this. We're going to factor this because, hopefully you saw this, when I factor it, one of my factors will be 1 plus cosine of x. So I'm going to factor my numerator. So I have 1 minus, so when it factors, I get 1 plus cosine x, 1 minus cosine x over this 1 plus cosine of x. Okay, we can simplify. These factors will cancel. So now all I have is 1 minus, and then I have this 1 minus cosine of x. And 1 minus 1. Oh, I made a mistake. I was going to say it's not going to equal it. Let's be careful here. Let me do this step. This is still in parentheses, and I almost messed up because I didn't distribute my negative. So I have 1 minus 1, and then this will be plus cosine of x. And 1 minus 1 is 0, so these cancel each other out. So all I'm left with is cosine of x, which equals cosine of x. So I was able to get the left side to equal the right side. So I did prove this. Okay, and obviously, like anything in life, the more we practice it, and the more you do these, the more you see like the tricks and what is used when on how to manipulate these. Again, there's not just one correct way to do these. There's 5 bajillion correct ways to do these. So you just got to keep manipulating until you get it to look like the other side. All right, so looking at 8, hopefully you guys are identifying. Left side is more difficult because of the subtraction. Okay, left side is more difficult because of the subtraction. When in doubt, I would change things to sines and cosines. I always think that is easier, the easiest thing to do, and it's always a really good tip. So I'm going to change this side to sines and cosines. So I know cosecant is really 1 over sine. So I have 1 over sine theta minus sine theta. All right. We want to get rid of these 2 separate fractions. We want to combine this into 1 fraction. So in order for us to combine to 1 fraction, we need to get a common denominator. So my common denominator between sine and 1 is sine. So that means I need to multiply this by sine theta and this by sine theta. So now I have 1 over sine, and we're going to combine them. So let's draw our common denominator is sine theta. So I'm going to have 1 minus sine squared theta. Hopefully you guys are recognizing right away what I have here. This is a Pythagorean identity. And 1 minus sine squared theta would be equal to cosine squared theta. So now I have cosine squared theta equals over sine theta. Okay, and then look at what your answer is. Cotangent over cosine. Well, we know cotangent is cosine over sine, and we know cosine is just cosine. So I'm going to split this. So when we split this, I'm going to write this as cosine of theta over sine of theta times cosine of theta. This is the exact same because if I multiply this back together, I get cosine squared theta over sine theta. And now we know cosine over sine, due to the quotient identity, is cotangent. So cotangent theta times cosine theta is equal to cotangent theta times cosine theta. And we proved it. All right, I want you guys to try the last one on your own. I will tell you the right side is more complex just because of the plus sign. Okay, so right side more complex. And notice how similar the right and the left side is. Okay, so you guys are going to manipulate that, and obviously you're going to have to get like a common denominator. You're going to have to do the whole thing to make it look like the left side now. So go ahead and give it a try. All right, so I'm going to start again. I'm going to go into sines and cosines, changing it to sines and cosines. It's just easier for me to understand. So secant is cosine, so I have 1 over cosine squared x plus 1 over sine squared x. All right, let's get rid of 2 fractions. Let's make it 1 fraction. So let's go ahead and get a common denominator. My common denominator would be multiplying those together. So let's go ahead and multiply those together. So we'd have cosine squared x times sine squared x. So that means I need to multiply this numerator by cosine squared x and this numerator by sine squared x. 1 times sine squared x is sine squared x plus 1 times cosine squared x, cosine squared x. This right here, Pythagorean identity, the most common one, a squared plus, or not a squared plus b squared equals c squared. This is sine squared plus cosine squared equals 1. So my numerator equals 1. So my numerator is now equal to 1. So I have 1 over cosine squared x, sine squared x. Okay, again, look what I'm trying to get here. I'm trying to get secant squared x, cosecant squared x. So to get that, I can just split these fractions. So I have 1 over cosine squared x times 1 over sine squared x. And finally, the reciprocal function, 1 over cosine is secant squared x. 1 over sine squared would give me cosecant squared x, which I believe is my left side. Yes, it is. So secant squared x, cosecant squared x. So I proved this. So qued. All right, and that's going to go ahead and conclude our notes for Trig 10. You could try not to get frustrated with these. There's a lot of different ways you guys can manipulate. Just use some of these tips and tricks from the first page to help you start manipulating and seeing what you can do with these different identities. I hope you guys all have a wonderful day, and if you need help, always jump on our office hours.